Okay, welcome to day 16. Today's assignment is solving trig equations worksheet number 4. You're going to use the formal trig identities quite frequently to help you solve here. So it's probably useful to have a list of those identities in front of you. You'll need the sum and difference identities for sine, cosine, and tangent. And you also need the double angle identities. The thing that you should know about these identities in general is they tend to pop up a lot of times when trig equations are involved. Maybe it's today with solving or tomorrow with inverse problems, but more likely it'll be later on in calculus if you're trying to do an integral or a derivative. These identities might be the key to make the problem much simpler. Also later on in linear algebra, if you're trying to rotate an object by a certain angle, maybe you want to repeat that rotation a couple times. Double angle identities prove really helpful there. So keep in mind that they exist, and when you need them, look them up, have them handy. So solving worksheet number 4, I was going to show you a couple examples to get it started. First, a familiar example. We've seen this one before. Cosine plus sine equals root 2. When we did it before, we isolated either the sine or cosine and then squared both sides. I just want to show you what would happen if you squared both sides right away. So that you had cosine plus sine all squared equals root 2 squared. The binomial on the left, when you square it, you get cosine squared plus twice the middle term, 2 cosine sine plus sine squared. And then on the right, when you square the root 2, you get a 2. Of course, on the left, we see the Pythagorean identity. Sine squared plus cosine squared is equal to 1. I'm flipping the order of that middle term, and you can probably guess why. I subtract 1 from both sides so that I get 2 sine x cos x equals 1, right? And then when I get down to this step right here, what I'm recognizing is the structure of sine's double angle identity. That is sine's double. So having that list next to me really helps. Say, okay, yeah, I can use that right there. So I can substitute sine 2x where 2 sine cosine was before. So I go from 2 trig functions multiplied together, sine times cosine, to a single one. And then to solve sine of 2x equals 1, I just ask, where is sine equal to 1 on the unit circle? So that would be at pi over 2 plus all multiples of 2 pi k. And then from there, I can simply divide by 2 and get pi over 4 plus all multiples of pi k. One catch, of course, because I use the squaring both sides technique, you do have to worry about possible extraneous solutions, and we are getting them when we add 1 pi. So it ends up being pi over 4 plus 2 pi k because of the extraneous solutions. Okay, let me show you another way to do this same problem that uses a different identity, probably even in a more creative way, that avoids extraneous solutions altogether. This is one that I think a lot of people wouldn't think of on their own, but as you come up with more and more practice, you start to see the relationships between these things. Maybe this is an idea that pops into your head. So instead of squaring both sides to start, what I might do instead is divide both sides of the equation by a root 2. Divide by root 2 on the left and the right. So what that means for the cosine is cosine's divided by root 2, or we could say it's multiplied by 1 over root 2. And then I do the same with the sine. And of course, if root 2 is divided by root 2, I get a 1. Okay, so that looks like I just made a big mess. But I know in my head that 1 divided by root 2 is the same as root 2 over 2, a very familiar value from our work with the unit circle. So I can write it that way if I'd like. Okay, and now I also know the reason that I'm so familiar with root 2 over 2 on the unit circle is because that's sine of 45 degrees, or cosine of 45 degrees. So I'm going to substitute those into my equation here and here. So I would write this as sine of 45 degrees times cosine of x plus cosine of 45 degrees times sine of x equals 1. And maybe at this point, this madness is starting to make a little bit of sense. What I've created out of thin air, sort of, is an angle sum identity. I have sine of the first angle, cosine of the second, plus cosine of the first angle times sine of the second. So this is really an example of being very, very creative with mathematics. How can you take something where it doesn't look like, structurally doesn't look like any of these, right? And how can you kind of create it? Well, we just did, right? Took a few steps, but we did it. That means I can replace this big monstrosity that I created on the left-hand side. I can replace it with sine's sum. So this would be sine of 45 degrees plus x. Sine of the first angle plus the second, alpha plus beta. That would equal 1. Okay? And now I'm ready to solve, because sine of some angle is equal to 1. I know that sine's equal to 1 at, let's work in degrees here since I use 45, up at 90 degrees. So I'd say my angle, 45 degrees plus x, is going to be equal to 90 plus all these multiples of 360. And all I have to do now is subtract 45, and I've isolated my x. So x is equal to 45 degrees plus 360k, which was the same answer we had before with the pi over 4 plus 2 pi k once we threw out the extraneous solutions. But this time, we don't have to eliminate any extraneous solutions. Cool. Let's look at one more example. And see where we can go from there. Okay, so in this one, we want to look at actually an inequality. This is example 2. So a few inequalities on the sheet. My recommendation with inequalities is do them with algebra and with graphical techniques. So cosine of 2x is greater than or equal to sine of x. And again, minimal space here. What we're trying to do is we're trying to find the x's where this is true. Okay? And let's just say, let's work on the interval from 0 to 2 pi. So I'll make that little note up here so I don't forget. On the interval from 0 to 2 pi, where is cosine of 2x greater than or equal to sine of x? Okay, so graphical techniques. Okay, let's just color code it as best we can. Looking at blue and purple, I hope you can differentiate between these two. Cosine of 2x, I'll graph in purple on the interval from 0 to 2 pi. So you know what cosine looks like, but we need 2 of those. So here's a second one, because its frequency is 2. And then, meanwhile, sine of x on the interval from 0 to 2 pi would look just like this. Maybe like that. Okay. So what I'm trying to find here is where is the purple greater than the blue? Where is cosine, this first curve, higher than the second curve? So I can see a few values right off of the start, from 0 to whatever this value is right here. Okay, so the question becomes, what are these intersection points? Once I can find these intersection points, then I think I can more clearly see where is the purple greater than or equal to the blue. Okay, so I need to find the intersection points. I need to solve. So the question becomes, where is cosine of 2x equal to sine of x? Okay, now you see why you need a double angle identity. Cosine has twice the angle, and sine just has the angle. So we get to choose a cosine double. Anytime you get to choose a cosine double, make sure you consider all 3 possibilities. So the first possibility, I could substitute here cosine squared minus sine squared for cosine's double. Okay, and you think, is that a good choice? Well, a good choice would be one that gets you down to just a single trig identity, maybe just sine, right? That didn't do it because I have a cosine squared here. No trouble, I could just then use my Pythagorean identity to sub in for cosine. But it is a bit more efficient to use the, perfect version of cosine's double right away. So cosine of 2x is equal to 1 minus 2 sine squared. So now 1 minus 2 sine squared is equal to sine. When I group everything on the same side, I get the quadratic form 2 sine squared plus sine minus 1 equals 0. I believe that factors. So we say 0 is equal to 2 sine x and sine x. And then we get a minus 1 and a plus 1, just like that. That's great. So then I find out that either sine x is equal to a half or sine x is equal to negative 1. Okay? Where are those true? Squeeze a unit circle down here. Either sine is negative 1. That would be down here at 3 pi over 2. Or sine is a half, and that would be up here at pi over 6 and 5 pi over 6. Okay, so I got my 3 solutions where these are equal. What I do now is I usually come back to my graph and say, all right, I see where the curves are crossing. Let me use those to figure out where the purple is greater than the blue. The cosine 2x is greater than the sine of 2x. So my 3 values are pi over 6, 5 pi over 6, 3 pi over 2. I'm just going to label those on my graph here. I can see the first one right here must be the pi over 6. The second one right here, that must be the 5 pi over 6. And the last one right down here, that's pretty clearly 3 pi over 2 when sine hits its minimum. Okay, so what I can do now, let's erase the work here. I can say that cosine of 2x, which is my purple curve with the frequency of 2, is greater when x is in the interval from 0 to pi over 6. That's the first part here. Now the blue's greater for a little while. Union 5 pi over 6. And now I'm not going to actually stop at this intersection point right down here at 3 pi over 2. 3 pi over 2, they're equal. But afterwards, the purple's still greater than the blue. So 5 pi over 6 all the way up to 2 pi. And I'll use a regular parenthesis around 2 pi because of the directions. Okay, hope that gives you a little bit of help solving trig equations worksheet number 4.